Okay, we are now going to get started with the last session of the day. We're going to hear from two project speakers this afternoon. The first is Fred Moolekamp, who will talk to us about project plans for deblending, and the second is Jim Bosch, who will talk about plans for building and using coeds. Okay, Fred, it's all yours.
Okay. So I'm going to talk about the project's plans for deblending. And so, a lot of times I have to give kind of a detailed introduction, but judging by the fact that this seemed to be the topic that the majority of the people want us to talk about, I think that, we all have a pretty good idea what I'm talking about, but I'll still, give my kind of brief introduction, right? So what's the problem we're trying to solve with the blending? Well, space is big, right? But it's also filled with stuff. And the deeper the images we take, kind of the more stuff that we see that it's filled with. And so, we notice that as we take longer exposures, we start to see more and more galaxies and stars and things that overlap. And so that if we look at any one pixel, it becomes more difficult to figure out where the light in that pixel is coming from. So there's a simpler problem, easier in the sense that if we look at crowded stellar fields, right? So that's something, like a cluster or in the galactic plane, where the majority of the sources are stars. This is mostly a solved problem. And so Colin's going to talk a bit more about our plans for crowded stellar field photometry on Thursday, so stay tuned for that. The reason this is an easier problem is because stars are point-like. And so that means we can model them. And that model is essentially the model of the PSF. And so essentially we can have an iterative solution where we model the PSF. We model each source as some multiple of the PSF with varying amplitudes and position. We can subtract the sources that we've already modeled. And then we can look at the residuals and detect new sources. And so again, kind of modeling the PSF can be tricky. And figuring out exactly how to do detection on residuals is a little bit tougher than it sounds. But compared to galaxy deblending, this is a much easier problem. So most of this talk is going to be about things that make galaxy deblending galaxies impossible. So for one thing, galaxies vary in morphology, and they have no sharp edges. So for example, if you look at this image, even though this is a strong lens, and so there's going to be other effects going on in here, you can still, see that we have galaxies where you have this really faint region in ellipticals where the flux kind of goes out, very far, and you don't know exactly where, your aperture should cut off to include all of the light from that galaxy. You have, very complicated morphologies of spirals and irregulars. So in addition to that, the Rubin Observatory is going to be looking at images from the ground, and the ground-based PSF is going to make blending worse. And so in this image, we see some figures from Will Dawson et al. The 2016 paper, and notice that in the HST, in the Hubble Space Telescope columns, right, you see a lot of cases where you can clearly detect two distinct sources from space, but because of the wider ground-based PSFs, now we see those blended that are only being detected as one source. And so blending becomes worse just because we're on the ground. We also have instrumental and astrophysical backgrounds, right? So Yusra is going to be talking about these tomorrow. So an instrumental background, for example, would be something like this bright star where you can see, the wings of it that are different in different bands. Astrophysical backgrounds would be like the inner cluster light. And so, or, what's background to some people, for example, low surface brightness galaxies, obviously isn't to others. Another problem is that if we want to calculate what the center of an object is, the so-called centroid, that's going to be shifted due to the presence of neighbors. So any kind of algorithm that relies on knowing where the center of a source is, this is especially difficult for some of the neural networks and machine learning algorithms, is you can't say exactly where the center of a source is to have a perfectly centered galaxy, just because the presence of neighbors there is causing that location to shift. And galaxies have optically thick regions, right? We can't just think of an image as the sum of all of the galaxies and stars in it, because there's going to be dust in galaxies. And so sometimes when you have overlapping galaxies, there's going to be regions that obscure what's behind it. And so in these cases, you can never perfectly recover the flux from the galaxy that was in the back, because it's being blocked by something in the foreground. Okay, so how bad is this problem? So on the left, we see some plots from HSC-wide data. And so these are two of the RC fields. And so you see in the wide data, it's not terrible. You know, I mean, we still have, 40 to 45% of the objects are isolated, which means, just over half are going to be blended. But most of those blends are small. And so, somewhere between, somewhere around 60% of the blends are going to be 2 sources or less. And 3/4 are going to be blends of like 4 or 5 sources or less. And it's only kind of like that last, 10% where you start getting blends that are bigger than 10 or 16 sources. Now in the deep data, it's, it becomes more difficult, because now only 23% of the galaxies are isolated. So now you've got more than 3/4 of the blends of your sources are going to be in blends. And, and 25% of those are going to be in larger blends that are 16 sources or more, and 10% are going to be in really large blends of more than 34 sources. So let's talk about a little bit about what deblending is and what it isn't. So it's an algorithm to separate flux and pixels with flux from multiple sources. But the algorithm that we implement is going to be dependent on what we want to optimize. So for example, we may say that we want to optimize photometric measurements for the majority of simple blends, right? So these are like kind of those 4 and 5 source or smaller blends. Another option is we could say we want to reduce the number of outliers. And so we want to try and not have as many catastrophic blends, but that may be at the cost of slightly degrading the measurements that we make on the majority, or it could be something else. Ideally, we'd like it to be an application of a minimal number of assumptions on galaxy compositions, because we don't want to bias our measurements on what we expect galaxies to look like any more than we have to. But deblending is not a unique solution, right? There are going to be, kind of degenerate solutions that can all give the same rough fit to the data. And so we have to have some assumptions and constraints that we put in there. But again, we want those to be as minimal as possible. And it's not expected to perfectly recover the flux of blended galaxies for the reasons that we mentioned, that doing that is just impossible. And we'll see in Jim's talk on Thursday, it's difficult enough to just measure, a galaxy that's isolated. And so blending has just made that even more complicated. So let's take a look at how deblending is working currently in the stack. And so this is implemented in the MES Deblender package. This was developed, I'd say it's kind of like a cousin of the Sloan Deblender. It was developed based on the Sloan Deblender, but it's a bit different. And I'll try and highlight some of the differences. So to understand the way the algorithm works, let's first take a look at a few different types of galaxies, kind of going up from signal to noise. So these are kind of the faintest galaxies. And, at low signal to noise, just about everything are kind of these elliptical looking blobs. We see, that they're roughly symmetric in the sense that if you look at the center of any one of these blobs and you look at opposite sides of it, the pixels have roughly the same amplitude. And they're roughly monotonically decreasing, meaning that they're kind of brightest at the center and the flux is falling off as they move away from the center. As we increase the signal to noise, we see that this, still continues for the most part. We do start to see a little bit of structure appearing in some of these galaxies. But even as we start to increase signal to noise enough where we start to find galaxies that we can see some structure, we still see that the rough ideas of symmetry and monotonicity are in most cases still observed. even as we get into some deeper images with even higher signal to noise, until we get some of these really big galaxies where we reach a point where we can resolve enough detail that now things are no longer symmetric and certainly not monotonic, at least not looking at the galaxy as a whole, even as one or two components. So the way that the current algorithm works is the first thing it does is fit each peak to the PSF. And this takes advantage of the ease of which we can model point sources. And so essentially it takes a box the size of the PSF, which in the HSC is about 41 by 41 pixels. And it fits the amplitude in the center of that object and any other objects, any other neighbors that may have some flux in that same box. And if it has a small enough chi-squared, so if it's less than 1.5 per degree of freedom, then that source is flagged as a PSF source. And then the next several steps, it's basically going to skip this and go to the part where it actually reweights the data. So one of the issues with the way that it's implemented in the current stack is this isn't done consistently across bands. So the MES Deblender package is explicitly run on single band images. And so whether or not a source is deblended as a PSF can matter. And so, for example, in this particular blend, sources 9 and 11 are the only ones that were consistently labeled as a PSF source. Now, this is different than the Sloan Deblender that tried to match everything to the PSF and then came up with a consistent model across all the bands. But you can see why this is useful if you look at something like source 9, where we've modeled as a PSF. If we built a template in the same way that I'm going to describe the next few slides, this is what it would have ended up looking like, this middle column here. Whereas if you look on the right, this is the PSF model that was built in the stack. And so, especially for really faint sources, it's going to help us to do a better job of correctly weighting that flux. For all the remaining sources, it's going to build a symmetric template. So essentially a twofold symmetry. So again, this is like if you look at source 2, it's going to look at the flux at the center of the source. And then for any pixel, it's going to look at the pixel on the opposite side of the center, and it's going to take the minimum of a flux of those two pixels. And so the reason this works is you can imagine source 2, it's again, because we know the galaxies are roughly symmetric, it's using the fact that there's no sources on kind of the top left and right sides of it. And so it uses that to constrain what the shape should look like on the opposite side. And so for source 2 in this blend, we see that it does a pretty good job separating out this source from 3 and 4. But for the other sources, we have a problem, right? For source 4, because there's a point source kind of down here and to the left, and it has a source to the upper right, you start to steal flux from both of those objects because symmetry is not a strong enough constraint to isolate this object. So the next step is going to be to ramp up the flux at the edges. So in this case, none of these blends are on an edge, but if they had been, then we would slightly grow the footprints to make sure that we're also trying to model the edges of these galaxies. And then it applies a median smoothing kernel, right? And so this is something that wasn't done in the Sloan Deblender, but essentially it takes a box, a 5 by 5 box that's centered on each pixel, and moves that and uses that to calculate the median that it assigns to any pixel value. So you can see how we're slightly degrading the data at the cost of making it look slightly smoother. And then the next step is to make the flux monotonically decrease from the peak. So this is trying to help sources like source 4 here, where you start to have kind of a secondary peak caused by objects on opposing sides. It's the so-called 3 in a row problem. And so if you look at the kind of the wings here in source 4, you can see how it's helping to suppress the flux that it's going to be stealing from its neighbors. And now the last step is to reapportion the flux. And so what it does here is it takes all of the templates, even the point source templates, And it uses those, the ratio of those in any one pixel to reapportion the flux. So if you look in one pixel, so this pixel over here is probably only going to be in source 2. And so all of the flux in that pixel would be attributed to source 2. Whereas pixels in the middle between all three sources, it's going to be distributed to each source based on the ratio of the templates in that pixel. And so again, you see for source 2, it did a fairly good job separating out the flux from its neighbors. Whereas source 4, you can see that we're stealing some of the flux from this point source that's down here to the left. Now, one of the issues with the current Deblender is that stray flux isn't included in any of the sources. So that means when you build your symmetric template, if you had an asymmetric galaxy, for example, that might have some flux over on the side, that's not going to be included in this source because it was outside of the footprint of this model. And so they found when they were running this on HSC data that they were having issues where this was actually doing more harm than good. And so there's some light that's just not included. But this works shockingly well, right? Remember that about 60% of the blends, or about 65% of the blends in the wide data only have, 2 objects or only a single object in them. And so for most of these, it does a pretty good job. You can look at this blend here in the top right, where you see kind of a wider orange galaxy that has another one overlapping with it. Again, it doesn't do a perfect job deblending here in the overlap region, but the colors are roughly correct. And so that means, for example, something like photo Z, that it should do a decent job recovering those measurements. But there are still some problems with this algorithm, right? One of them, as I mentioned already, the PSF fit's not consistent across bands. Now that's something that was done in Sloan and something that could be implemented. It just hasn't yet. Also, galaxies are not actually symmetric, right? They're close, but they're not perfectly symmetric and they have dust. So this can result in poor reapportioning of flux in blended regions. The outer regions of asymmetric galaxies are ignored as stray flux. And again, this wasn't done in Sloan, but this was a decision that they made based on the HSC processing with the current Deblender. And the 3 in a row problem, right? This problem where when you have 3 sources kind of in a row, and this argument of symmetry breaks down, is going to increase as images become deeper. Also, undetected sources undetected sources are included in our flux measurements, right? If we have 2 sources that are ambiguous blends, and we don't detect one of them, because this algorithm reapportions all the flux, it's going to add the flux from those undetected sources into the flux from another source. And because we're reapportioning all the flux, there's no residuals. So we can't do like we did in crowded field photometry and subtract off everything we modeled and go back and look at the residuals. So we can't do any kind of hierarchical deblending with this method. And one poorly deblended object will steal flux from multiple neighbors. And so here's an example of that, a few examples of that, where you see, you have kind of one object that has galaxies on both sides. And so now it's stealing light from both of those, but now that means that, all of those sources also aren't including all the flux that they should, even though, they were only blended on a single side. So this, becomes a catastrophic failure mode for this type of deblender. So let's look at what other people are doing. So source extractor is kind of, is a widely used out, package for doing, detection and measurement of fluxes for stars and galaxies. And so this performs detection. It doesn't really deblend. What it really does is it generates a segmentation map. And so that means that any one pixel is based on its distance and the way that it's located compared to the other sources is assigned to one source or another. And so this works really well for sparse exposures without a lot of dynamic range. But if we start looking at galaxies, where we have a lot of dynamic range and some of these kind of like these brighter galaxies like source 19 that you see in this blend, you see that all these little smaller neighboring stars and galaxies just kind of eat away at its flux because the pixel is only assigned to a single galaxy. And so that's not really the blender, and it's not ideal for being able to make detailed measurements. So other Deblenders have taken a Sursich model approach, right? So they'll essentially, model galaxies that bulge in a disk, often, divoculars bulge with an exponential disk. And then you can proceed kind of more similar to crowded field photometry, where you can fit right up parameters like the ellipticity, the angle, in addition to the position and the amplitude. And so GalFit is an example of this, where they use a parametric model, but then also, make their models slightly more complex so that they can add some bending modes and some other features to try and better model realistic galaxies. In the Dark Energy Survey year 3 processing, they used the multi-object better. And so this used a bulge disk model, but they used Gaussian mixtures to actually model it, but found that it didn't work well in crowded regions. And so for the year 6 processing, they moved on to the shredder. And this is the unofficial logo that I've adopted for them. And so the shredder base is what's used in the year 6 processing. The multiband model, so it's a multiband model with galaxies as, n free Gaussians, but they all have a fixed center. And so this works better in crowded regions. And so there, the neighbors are subtracted. The resulting clean image is then fed to a more precise modeling code. And so this is what they're using in their year 6 processing. So now let's look at what the leading candidate is for the DM pipeline. And that's the blending with a package called Scarlet. So this is something that I've been working on with Peter Melchior, who's a new faculty member in Princeton. And so, as Peter begins to, kind of increase his number of postdocs and students, we get to take advantage of the fact that we have both someone on project working on developing this package, as well as, somebody off project who can, kind of put in some, more features that we don't have, the time or the money to be able to implement. And the basic idea behind Scarlet is that, with the exception of the multi-object fitter and the shredder, all of the blenders I just talked about were looking at a single band. So this would be like a single band HSC image, whereas Scarlet now tries to look at the image as, looks at all bands at the same time, right? Because we know that with our eyes, we can look at the color image and we can see where the blue galaxy, the blue disks and the blue stars pop out from the orange galaxies. We can see, the reds and the blues in contrast. And so it makes it much easier for our eyes to deblend. And so it's up to us to try and get the computer to do the same thing. So the basic Scarlet model is that we define an initial multiband model for each source in the blend. Now, the blend model exists in a frame or kind of a scene that has a very narrow PSF. And so that's what you see in the lower left-hand corner here. And the advantage of this is that in this this narrow PSF, often most of the objects aren't actually blended together. And so it's only when we convolve that model to match the observed scene that now we start to see more increased blending. And so we forward model to the observed data, to the observed frame, and then we can compare that to the data. And so Peter came up with an algorithm, AdaProx, which is an implementation of an adaptive gradient method. And so essentially the way this works is we build the model, we convolve it to the observed scene, we look at the difference between that and the data, and then we use that to give us a gradient step that then we back propagate through our algorithm which is just saying that we can pass those algorithms through in a chain rule-like way back to the original parameters of our model, and we can update that and we can repeat those steps until we converge. And so the basic model, you can think of modeling this entire blend where every source just has one component in it. And that component has a single SED. And then every pixel in its morphology is given that SED. And then again, this is the model that you see here, the rendered model, where we've taken these sparse models that you see in each of these little postage stamps, inserted them into the model, and then convolved them to match the data. But now we can also put in multiple components. So for example, in the top row here, you see the model frame. In the bottom, you see the observed frame, where now we can have, the first component, which looks like it's roughly the disk of this, spiral type galaxy. And then we add in a second component for the bulge, and then that gives us a full model for the source, which then we can look at the data and again see that we did a pretty good job isolating this object. We can also model objects as point sources, right? So if we have reason to believe something's a point source, either because we've measured proper motions or we've come up with some heuristic that can allow us to say that we are certain that this is a point source, then essentially we have our PSF model, which is it's this gray, very small, narrow PSF that then we can convolve to the observed PSF and shift it to the location in the image. And so if you look at this, this particular blend here, modeling the first source as a point source, you can see that it did a good job. We don't see any effects from the residuals. But now, unlike the current Deblender, we can actually see that there's an undetected source that was right next to it. And so if we went back and ran detection on these residuals, we could model this source and go back and go through this procedure again. Another type of model we've been looking at is implementing a neural network. So Francois Lanous has been working on looking at training a neural network on isolated real galaxy templates, and then using a pixel CNN, which basically gives you kind of a likelihood for each pixel based on the other pixels in the morphology. And so now we should be able to have realistic constraints on what galaxies look like. Now, this is something that's not really implemented in master and Scarlet yet. This is something that's still in development, but you can see from the example image here in the top right that the residuals look really good when we can, even for complicated galaxy blends. And we can have other possible models, right? We could implement a parametric model. We could implement a Gaussian mixture model, or a multiplicative dust model, or other custom models by the user, because each source doesn't necessarily have to have the same model. And so it may be that we can develop some clever heuristics to decide which different types of models to use for different types of sources, and what measurements we plan on making. And so just to compare it to the stacked Deblender, so on the left here you see the results of this, this complicated blend using the stacked Deblender, and then in the middle we see Scarlet's model in the model frame for sources 2, 3, and 4. The rendered version, and then the actual observation. And so you can see that we're doing a much better job just capturing the flux in any one of these objects without stealing too much from its neighbors. And as I said before, the nice thing is Scarlet residuals can be useful, because now if we've done a good job modeling all the sources in the image, then we can go back, we can run detection on the residuals, and we can find things that we missed, right? So now Scarlet can perform more like a crowded field code, and that we can have this iterative procedure of detection and deblending. And then just here's another quick example, again, showing that we, even in the 3 sources in a row problem that would give the current Deblender fits, we can model all the sources in the blend with effectively nothing left in the residual. Also, just to show a quick comparison, so this is what, I don't want to go too much into measurements. Jim's going to be talking about that later this week. But without going too much in the details, this is roughly the left-hand, the plot in the upper left is the current Deblender running galaxy photometry. And so the y-axis is the difference in millimags from true injected sources. So we took some HSC images, we injected sources into those so that we have a true value for them. And these are the results you get with the current Deblender. In the middle, this is Scarlet from last year. And in the right, this is the newest version of Scarlet this year that implemented Peter's new algorithm. And so you can see, we were already doing better last year, and we significantly improved things even just in the last few months. And in the bottom left, so each of these lines here is the median absolute deviation in the different magnitude bins. And then at the bottom, this is essentially just plotting those same lines, but now on top of each other on a log scale. So we can see, so we can have a comparison of how the current Deblender is doing versus Scarlet. So we have a number of upcoming improvements. So we want to be able to do better identification of source type for initialization and model choice. That should improve both the CPU performance, the runtime, and it should make it more robust. We're looking at implementing analytic convolutions. So right now we're doing everything in K-space. And the Fourier transforms seem to be really difficult to backpropagate our gradients through. So we're thinking that implementing analytic convolutions is going to be faster. And it's not clear right now, but there's a possibility that because this backpropagating of the convolutions is essentially a deconvolution algorithm, it could be giving us trouble for some of the when we have higher frequency modes in our initial models. And so this also could give us improvements in robustness, but we don't know that for sure. We're looking at possibly being able to do analytic gradients, and as to whether or not that's going to be faster than just using AutoGrad. Again, this multi-scale or iterative detection and deblending problem, where we can model the brighter objects, subtract them off, and model the fainter objects. We're looking at being able to improve constraints and new models, right? So some of the things that Peter's group's working on is looking at things like modeling dust, modeling low surface brightness features, modeling jets. And so as they come up with new algorithms and update the code on that, we get to take advantage of all of that in the Rubin Observatory. Okay, so some more distant improvements, right? It may be that the Deblender that we're using in year 10 isn't the same as what we're using in year 1. So, for example, one of the things is being able to prevent detection and deblending from shredding large spirals. It's a non-trivial problem. But it would be nice to be able to have some heuristic that we can go back and look at certain types of blends and identify that this is actually one object, this is actually a spiral, and put those pieces back together. We could potentially model the PSF during crowded field deblending. And we're looking at being able to train and test deep learning solutions, right? So this would either be potentially like Francois Lanous's Pixel CNN prior that I mentioned a few slides back, or this could be, something even more, more ambitious, like the variational auto-encoder deblending that Arsalan et al. Have written up recently. This is going to require a robust training and validation sample and testing on real images. So these types of solutions really aren't likely to be implemented until mid-survey at the earliest. But it's worth keeping in mind that that there may be some more advanced features that we can try to put in later. Kind of a final note is keeping in mind the different types of deblenders, right? So when we say deblender, Robert would say a deblender is an algorithm that produces images that can be further analyzed. So the philosophy is basically there are measurements we want to make that must be made on data, not on models. And so he gives examples of Gini coefficients and Petrosian magnitudes as measurements that we may want to actually make on data to blend it with what he would call a deblender. This would be something like the Sloan deblender, the current stack deblender. Maybe you could consider source extractor in this category, although again, it's really just creating a segmentation map. And then the other type would be a simultaneous fitter, right? And so this is doing simultaneous model fitting and measurement of multiple sources. And so the philosophy, basically, we need to have a model to know what we're measuring. So for example, we may want to measure flux, colors, shapes. And so examples of this would be like MOF for the shredder, GalFit, crowded stellar field codes, or Scarlet. And it may be that we need both different types of deblenders. And so that's something that's kind of being internally discussed. So in summary, deblending is a hard problem. The current deblender does well for simple blends, and we've been making a lot of progress in simultaneous fitting stars and galaxies using Scarlet. But we need to run more extensive tests for shapes and biases compared to the multi-object fitter, the shredder, so we can kind of compare to what the state-of-the-art other projects are using are. Scarlet allows us to take advantage of new features that are added by Peter's group. And it's worth keeping in mind that the runtime for Scarlet's always going to be more expensive than the current Deblender. This next part of this is kind of internally debated on. It may partially be offset by savings in measurement time. It may be that the measurements we can make on Scarlet models are good enough that we don't have to go into some of the details of measurements that Jim's going to be talking about later in the week. But the bottom line is the project's going to use whatever Deblending solution works best that we have the compute power to support. And again, that may change over time. But this is essentially what I wanted to present to everybody to give you an update on where the Deblender is. So thank you.
Thank you, Fred, for that very good talk about deblending and project plans. Do we have any questions? I see there's been a small amount of discussion in the Slack channel.
Okay.
Rachel, would you like to trigger the discussion you've started in the Slack channel? Oh, everyone's putting their hands up now. Just a second. Let's see where our list is. Okay, let's start with Raul, who has a question, who has his hand up.
Yeah, so I actually don't want to discuss the shredder thing again, but I was wondering if you have any comment on strongly lensed galaxies and whether that's a case that you consider. It's a rare case, but is that something that you think about what's going to happen to them when you pass this through your Deblender?
Yeah, so that's a good question. So are you talking about just measuring like just a single galaxy, or are you talking about like kind of multiple representations of the same galaxy in a lens?
I'm thinking of essentially galaxy lenses,
Mm-hmm.
and whether they can be detected later on, and whether this Deblender is going to already do something to them before speech.
I mean, I guess I can't say for certain. I mean, I wouldn't imagine that that's something that we would be identifying internally in the Deblender, unless it got really sophisticated really fast. We try to put constraints on our models that will be that won't be so constraining that they would prevent us from modeling a lens galaxy. But I think that's as long as we can roughly model them as well as anything else as irregulars and other oddly shaped galaxies. We'll do the best we can for that. But at this point, I think we're mostly focusing on trying to get the majority of blends and galaxies down, and then as we have time, as we get closer to the first light, we'll be able to maybe look at more difficult cases.
Right. I wasn't expecting an identification as such, but I was wondering if this is a test case that we check what happens to these kinds of systems. Okay.
Yeah. This is something that at least Phil Marshall and I kind of touch base on about once a year. So it's something we're thinking about. But actually, I don't even think I have a lens system that I've run Scarlet on. So if you have an example and want to send it to me, I'd love to run it and see what happens.
Okay, thanks. I'll get in touch with you.
Cool.
Okay, Alexandra, you can go next.
Yes, hi. I would like to know how dependent on the initial centroid of the source Scarlet is, in the sense that when you update the models, do you also update all the centroids, or do you still keep them fixed?
So there's a few different ways we can do that. We can keep the position fixed. And so if there was some reason where we felt like it was a tight blend and we'd have the position kind of jumping from one source to the next, we could fix it. Typically what we do is we give an initial model, we calculate the likelihood, we backpropagate that and update all the models. And then if there's a new pixel that's the brightest model in the source, then we say, okay, this is our new scent. And so it'll allow the model to shift slightly, within one or two pixels per iteration. There's a more expensive algorithm where we can actually shift it, and so that the internal model for each source is centered, and then we shift it into the full scene model in each iteration. That's probably going to be far too expensive for the Rubin Observatory to be able to run, but it's an option that at least is there if we had to.
Sure. All right, thanks.
Mm-hmm.
Okay, we have a question now from Gary. Go ahead, Gary.
For you invited comparison on your last slide of the time that an algorithm will take to the time that's available on the computational system. Can you give a rough estimate of the order of magnitude of that ratio for Scarlet 1.0?
I can't, unfortunately. I had a feeling that this question was going to come. So usually when we talk about it internally, there's this question of, okay, how much time do we have to run the Deblender? Well, how much time do you need? Well, how much time we can have? And it's just right now it's in the circular argument phase. So right now it takes roughly 500 milliseconds per source. So roughly 100 milliseconds per source per band. And I think we've talked about, roughly in the past having, trying to get that down to roughly 50 milliseconds per source per band. But I don't think that even that number is set in stone. So I don't think there is anything set in stone yet, to the best of my knowledge. Jim or Robert could probably speak more intelligently on that.
Okay, we have a question now from Keith Bechtel. Keith, go ahead.
Okay, so I guess this is a two-part question. One is, what do you envision as being the primary validation methods for when you're applying the deep blending on actual data? And I realize that you already showed a couple examples in the slides, but just if you had additional thoughts on that. And then two, are there mechanisms such as flags or ways of highlighting additional uncertainty that would be indicative that the blend failed in some way, or there's some sort of problem in the deblending process?
Yeah, so I'll answer the second part first, because that's the easier one to answer. And that is yeah, we've definitely talked about that. One of the things is we can look at the chi-squared, we can look at the residuals and see how much flux is left over, and that's one indicator. There's some code that Peter's implemented that will give you some rough error estimates, and so that's something that we're hoping to make more robust and be able to start including. And then let's see, remind me the first part of that question again, Keith.
Oh, the validation methods for that you would apply on actual data.
So we don't have anything set in stone, and so we're kind of actively seeking input from other people on what what you all think we should do. Certainly running both the current Deblender and one of the something more high tech like the Shredder and Scarlet on images where we've injected fakes. And the nice thing about those, right, is because you have real galaxies in there that give us real galaxy deblending problems, but then the fake sources give us some truth value that we can compare to. And so I think that's going to be one of the strongest methods is doing both photometry and shape measurements on fake sources, and comparing those to to existing codes to see how we compare.
Thanks.
Mm-hmm.
Okay, so we have time for one last question now from Steve Kahn. Go ahead, Steve.
Yeah, so maybe you said this and I missed it. Could you comment on how you would use these methods to incorporate high resolution data, say from Euclid or from W1st, and improving the deblending of LSST data?
Yeah, so this is actually something that we're actively working on. So Remy Joseph is a postdoc at Princeton working with Peter, and he specifically working on multi-scale deblending. And so basically what we do is we have, this is one of the reasons that we switched to building our model entirely in this sparse frame, is because now we can convolve that up to any observation we want, and we can even do multi-resolution. So Remy has a paper coming up shortly on the algorithm that he came up with to do that. And so this is something that's, you know, Peter originally was working on W1st. And so from the beginning, Scarlet's always been designed as something that's going to be this multi-resolution, multi-scale deblender.
Okay, let's thank Fred again. Lots of claps on Slack for that presentation. Thank you, Fred. We'll move on now to Jim Bosch, who will talk to us about project plans for COADS.